Good morning. I've asked Ms. Escola to show you this audio/video because we've got a lot to cover with this unit, and I don't want to lose ground by just making this a study period. Also, I realized I skipped over some very important topics that I thought I had covered before Christmas break yesterday, and we need to cover them today so that we can get back to the unit circle, and you'll understand better what I was talking about yesterday. Again, we started with trig before the Christmas break, talking primarily about triangles. Now we're going to extend them to circles and connections with other aspects of geometry. But today, I want to back up, just talk a little bit about the angles on a circle or on a coordinate grid, and not worry about the unit circle too much today. First is review. Yesterday, we talked about two types of triangles, the 45, 45, 90 triangle, and then also the 30, 60, 90 triangle, which I have shown in two ways. One with a 30-degree angle on the side and the other with it up top. First, the 45-degree angle triangle. We have 45 there, 45 here, and a 90-degree angle. It is important to have these memorized, that if this side is 1, then that side's got to be 1, and using the Pythagorean theorem, you can come up with the hypotenuse being the square root of 2, because 1 squared plus 1 squared equals the square root of 2 squared, namely 1 plus 1 equals 2. And from there we get the basic trig functions, that the sine of 45 degrees is equal to 1 over the square root of 2. This is just SOHCAHTOA, opposite divided by hypotenuse, which is the square root of 2 over 2. The cosine of 45 degrees is also equal to the square root of 2 over 2. And finally, the tangent of 45 degrees, TOA, opposite over hypotenuse, is 1. If there are any questions about why you get those answers for those particular functions, please see me or ask me again on Monday. With a 30, 60, 90 triangle, here the angle is 30 degrees, there the 60, this one's 60, and that one's 30, so it's just flipped and turned on its side. We get the ratios that the opposite side is 1, then the hypotenuse is 2, and again, using the Pythagorean theorem, we get that that's got to be the square root of 3. Again, square root of 3, 1, and 2. And that, again, follows from 1 squared plus the square root of 3 squared equals 2 squared. Or 1 plus 3 equals 4. The trig functions that fall out of this are that the sine of 30 degrees, opposite divided by hypotenuse, is 1/2. The sine of 60 degrees is the square root of 3 over 2, and that's the cosine, sorry, of 30 degrees, sorry, getting ahead of myself. And finally, the tangent of 30 degrees, if you work it out, ends up being the square root of 3 over 3. With a 60-degree as your primary angle, you get that the sine of 60 equals the square root of 3 over 2. The cosine of 60 degrees is 1/2, and the tangent of 60 degrees, in this case, is opposite divided by adjacent. This one is different. It's the square root of 3. I'm going to leave it to you to look at these and make sure that they kind of make sense of the basic SOHCAHTOA argument, that you go opposite divided by hypotenuse and you get those answers, and that they do also fit with the Pythagorean theorem that a squared plus b squared equals c squared. If you've got questions, we'll go over it again on Monday if it is confusing. It does not play into today's lesson. I just wanted to show it to you one more time. And again, we will cover this on Monday if these triangles don't make sense. But those are basic trig functions that you're going to have memorized, both for it'll help you both on the ACT, and you definitely need it for calculus. So what's our focus today? Today, I want to just deal with trigonometric functions of any angle, that's a lot to say, and trigonometric functions of any real number for that matter, and I'm going to talk a little bit about periodic functions since we have not talked about these three things before. I'm going to save the 16-point circle till next week, so ignore that. We talked a little bit about it yesterday, but I'm going to just ignore it for now because we want to extend them again, the functions beyond basic triangles and open up a whole new world of applications, and that's the purpose for what we're doing today. First, some definitions. When you're talking about a trig angle, you again are talking about angles just like we did in geometry. You've got an initial side, and you've got what is called a terminal side and an angle. They call it alpha here. We could have just as easily called it theta or x or any angle measure you want. It just goes from, it's the measurement from one ray to the other. Just we're giving the rays sides, and we're calling it the initial side and the terminal side. Now, with what we're doing today, the initial side is always going to be on the x-axis. So this ray is going to be the initial side, and the other ray just depends where you go. In this case, that's the terminal side. And the angle is exactly what you would expect. It's going from the terminal side counterclockwise over to the terminal side. But you don't have to do that if you don't want to. If you decide to go clockwise, that's still the initial side. This is still the terminal side. It is perfectly acceptable to go clockwise. However, when we go clockwise and go the opposite direction, that is called the negative direction, and we actually get a negative angle. Let me show you what I mean with some examples. Not before I get to that. I can draw an angle, and I can go this direction, and I can call it, say, a 50-degree angle. And that looks to be about a 50-degree angle. If I want, I can go the opposite direction, again starting with the same initial side and going the other direction and calling it a 310-degree angle. Negative 310 because I went the other way. Either way, I end up at the same place. It's sort of like if you stand up at your desk right now and I ask you to turn clockwise, counterclockwise 50 degrees to your left. You can do that. I can have you end up facing the same direction if I say, now go back to where you were facing originally and turn clockwise 310 degrees. You'll still end up at exactly the same position. So whether I go counterclockwise 50 degrees or clockwise 310 degrees, so negative 310 degrees, so that's in the clockwise direction, so it's negative, you end up at the same place. That's important in trig because it's where you end up that is important. And it turns out that if you were to ask me what is the cosine of 50 degrees, you would end up with the same answer as if you plugged in what is the cosine of negative 310 degrees. And I'll do it really quickly on the calculator so that you can see what I mean by that. Again, either way, whether you go left 50 degrees or right 310 degrees, you end up at the same place, the same terminal angle, and as a result, it is the same result. Okay, clear this out, and I say cosine of 50 degrees, or I say cosine of negative 310 degrees. Same answer, either way. This gives rise in math to an idea or concept called coterminal angles. And coterminal angles are two angles in an extended angle measurement system, basically what we've just done, that have the same initial side and the same terminal side, yet have different measures. These are called coterminal angles. Going back to my example, I would say 50 and negative 310 are coterminal. I could also go around the circle one whole time, that's 360 degrees, and continue on another 50 degrees, and end up with 360 plus 50, or 410 degrees, and that would also be coterminal with a 50-degree angle. And if you check out the calculator and I say, well, what's the cosine of 410 degrees? It's the same value yet again. That's the idea of coterminal. So try a problem. If I ask you to find an angle that is coterminal with 45 degrees, so an angle that looks like this, are there other ways to end up at the same terminal side, to end up right here? That's the terminal side, either going in the negative direction or going more than one time around in the positive direction. The answer is yes. First, for the negative, I could start here and go around this way. How far would I have to go? Well, a complete circle is 360 degrees. 360 minus 45 leaves 315 degrees. So if I want, I could end up in the same direction by going negative 315 degrees. Again, I've got to go, I'm going in the negative direction, so I've got to put a negative sign, but negative 315 degrees ends up at the exact same point. The other thing I could do is go around in the clockwise direction more than one time. 360 plus 45, and I end up at 405 degrees. So, two ways to do it. I could either keep adding 360s, or really the better way to show this one is if you want to end up at 45 degrees, I can add as many 360s as I want. That would be coterminal. Add another 360 degrees, go another time around the clock, would be 765. Or I could subtract 360 degrees as many times as I want. Go the opposite direction, and you'd get the negative 315 by going in the opposite direction. Subtract 360 again. These would all be coterminal with it. Before we do it in radian measure, let's try another problem. I'd like you to try this one. Find angles that are coterminal with a 30-degree angle. Here's my 30-degree angle. And I'd like at least one of them to be negative. I'm going to wait a minute while you try this problem. Okay, one solution is to add 360, and you end up with a 390-degree angle. That would be coterminal. Go around for 360 and again, and 390 degrees is coterminal. Another solution would be to subtract 360. So I want a 30-degree angle, subtract 360, go a negative 330 degrees. That would be a 330-degree spin, and it's coterminal. Basically, think about any diver or something who's doing a 360 or 720 or 1080. They're just doing additional spins when they do their dive, and that's what you should think of when you're doing these angles. Adding 360 or subtracting 360 gets you to the same point. At this point, I'll let Mrs. Scola stop it. If you have any questions, and maybe somebody in the class would be able to answer it, if not Mrs. Scola herself. All right, let's go on to coterminal angles if you're dealing in radian measure. If you recall radian measure, 360 degrees is the same as 2 pi. That's going around the circle one whole time is 360 degrees, or 2 pi. You can do the same thing with coterminal angles by either adding 2 pi or subtracting 2 pi. And you can add as many 2 pi's or subtract as many 2 pi's as you want. Here the math is a little trickier, but you just have to find a common fraction. So pi over 6 plus 2 pi would be the same as 12 pi over 6. So you have a common denominator, and you end up with 13 pi over 6. Again, I just converted the 2 pi to 12 pi over 6. Add, since we have a common denominator, add the numerators. Pi plus 12 pi is 13 pi. Or you could subtract. Same idea. In this case, you get a negative 11 pi over 6. Just using 2 pi instead of 360 degrees. Okay, moving on. The next is the idea that we can get the trig functions by, and now we'll return a little bit to trig, by using a coordinate plane and finding a point on the plane and then finding the 6 trigonomic functions that have to go to it. So here's what I mean. We've got a point 3, 5. 1, 2, 3, up 5. 1, 2, 3, 4, 5. So it would be right here. I'll call that our point P. Our initial angle is always the x-axis going out that way. Our terminal ray, or terminal side, ends up being the angle that goes from the origin up to point P, which again is at the point 3, 5. Now, how we find the 6 trig functions is this way. We drop a side straight down to the x-axis. And the angle we care about is the angle formed by the initial side and the terminal side. That theta, there's our right angle. You can now label the sides opposite, adjacent, and hypotenuse. And since I know the point is 3, 5, I know the adjacent side, the x-coordinate, is 3. The opposite side is the y-coordinate, 5. And I can use the Pythagorean theorem to find the hypotenuse. 3 squared plus 5 squared equals 34. So the hypotenuse, h, has got to be the square root of 34. Since it's a squared plus b squared equals c squared. So if h squared is 34, then h is the square root of 34. Those are the 3 sides of the reference triangle formed by the point 3, 5, the x-axis, and the angle of the ray that goes through 3, 5. So we have a triangle. The trig functions just fall right out of SOHCAHTOA at this point. The sine is equal to the opposite divided by the hypotenuse, or the sine of theta, my angle in this case, is 5 over the square root of 34. We could rationalize that by multiplying by the radical 34 over 34, but I'm not going to worry about that right now. The cosine is the adjacent, 3 divided by radical 34, and the tangent of theta is TOA, opposite divided by adjacent, or 5/3. So basically, given any point in a coordinate plane, we can find the angle, theta, and all the trig functions that relate to it. They said find the 6 to find cosecant, secant, and cotangent. You would just do the reciprocals. Now, I'm not going to do that. All right, I want to skip that one. Here's the basic idea when you're given a point. We're going to draw the angle theta in the standard position, being careful to place the terminal side in the correct quadrant, because I'm going to do some that are negative coming up, and it might be negative. I'm not going to worry about where it is. I'm just going to label that point P and the origin. And then I'm going to draw a perpendicular line from my point P straight down to the x-axis, and it's going to form a triangle. And if the triangle's, based on where the triangle is, I just take my x and y coordinates and I put them in the appropriate opposite and adjacent sides, and then I use the Pythagorean theorem to find the hypotenuse. And then I just go from there. I think these instructions are a little bit more confusing than actually working a problem, so let's try one right now. Let's say that I would like to find the trig functions that involve the point -3, 4. Step number 1, find the point -3, 4 on your graph, over 3, that's -3, up 4, 1, 2, 3, 4. We get a point P right here, it's -3, 4. I'm going to draw the terminal side next. The terminal side goes from the origin up to that point. I know that this is my initial side, but I am going to actually draw a reference triangle by dropping it straight down like this. So it forms a 90-degree angle with the x-axis. I am then going to label my sides. This side is -3. I'm going to measure my sides. This side is 4. -3 because the x-coordinate was -3, 4 because the y-coordinate was 4. I now use the Pythagorean theorem to find the hypotenuse. -3 squared plus 4 squared, and the math on that is 9 plus 16, and that's 25. And so my side C, or the hypotenuse, has got to be the square root of 25, which is 5. At this point, I now know the 3 sides of my triangles, and I can find all of the functions that go with it, the trig functions. The sine of theta is the opposite side divided by the hypotenuse. This is still the opposite side on my reference triangle. It is 4/5. The cosine is -3/5, and the tangent, TOA, is 4 over -3, or -4/3. Now, I put my theta here as the reference, but these are really all of the angles that you would get with a theta that goes from the terminal side over to here. I just used a reference triangle to compute it. At this point, what I'd like for you to try are the exercises in the book on page 381, and they're going to, and just try problems 1 through 6. So page 381, numbers 1 through 6. And if this has been a little confusing, what I would do is go back to the beginning of the chapter on 4.3 section and read pages 370 to 373. 370 to 373. Problems 1 through 6 won't be due until Tuesday, so we'll have a chance to talk about them again on Monday, but I hope this has been helpful.